In Investigation 4, Problem 4.3, we're going to look at a special triangle called a 30, 60, 90 triangle and see some of the properties that it exhibits when we see triangles like this. But to do this, we're going to start with what's called an equilateral triangle, where all three sides are the same length. And in this case, we're going to say that triangle ABC is an equilateral triangle. And so if this side is 4 units, so we're going to say that each side is 4 units. And this full distance across would be 4 units. And so that gives us our equilateral triangle. And if we look at the angles on an equilateral triangle, each of these angles around here are 60 degrees each. And this one, because I've cut it in half, these are each 30 degrees. And then right here where P intersects, we have a right angle or 90 degree. So what it does is it creates two identical 30, 60, 90 triangles when you take a equilateral triangle. Equilateral meaning all the sides are the same length, equal sides. So this is an equilateral triangle. And if we look at some of the angles now, angle CAP, this angle right here, CAP is 30 degrees. And CPA, this one right here, is 90 degrees. And BAP is 30 degrees. So we have a bunch of angles. Angle BPA, this one right here, B to P to A, is 90 degrees. And the length of different parts, the length of C to P right here, so now if we only go halfway, that length is 2. And then from P to B, this one also is 2 because we just cut this 4 in half. And now to find the length of AP from here to here, this is now a shared leg between the two, and so we could take this hypotenuse and square it, and this leg and square it. 2 squared is 4. And if we take and subtract 16 from 4, we'll get the 12. And so this length here is the square root of 12. Now, if we simplify the square root of 12, which we can do, it simplifies to the square root of 4 times the square root of 3. And the square root of 4 is 2. Square root of 3. So this center piece here is 2 square roots of 3. So these are equivalent amounts. And we want this amount because something happens with 30, 60, 90 triangles. This center line, or this leg of the triangle, always will have the square root of 3 as a factor, and then the base leg is the other factor. And then the hypotenuse side, simply because we cut this in half, will always be twice as much as this. So when we look at the next problem down, now we're saying, well, what if we just say this distance here, side length is x units long. So that means that this side length is x, and then all the way across the bottom would be x. It's an equilateral triangle, so they're all the same. And that doesn't really affect the angles. All these angles still remain the same. 30 degrees, 60 degrees, and 90 degrees. So it doesn't change any of the angles. So if we look at all these angles, nothing has changed here. CAP is still 30 degrees. This one's still 30 degrees, 90 degrees, 90 degrees. Because no matter how big or small the triangle is in terms of side lengths, if it's an equilateral triangle, the angles will remain the same. And now our lengths are a little bit interesting. When we look at from C to P, you think about if the whole distance is x, then this is x over 2 or half of x for this distance. You could write it either 1/2 x or x over 2. I'm going to write it as x over 2. And the length from P to B is again the same thing, x over 2, or this time I'll write it as 1/2 x. They're the same thing. And now that we know that this length is x over 2, we know that the center A to P is x over 2 times the square root of 3, because it's always a factor, whatever this base leg length is, times the square root of 3, which we saw in this upper one. The base leg was 2, and then so this is 2 square roots of 3 tall. And that's always true on a 30, 60, 90 triangle, that leg is a factor of the square root of 3 times the whatever the base leg is. So we look at one more example, and this time we've eliminated the other half of the equilateral triangle, which would be out here, and just said if we start with this length of 6, we know this one is half as much, so it would be 3, and that this other leg would be this factor 3 times the square root of 3. And we could actually prove that if we take 6 squared, which is 36, and 3 squared, which is 9, and take 36 minus 9 is 27. So this is equal to the square root of 27. So we're just using the Pythagorean theorem now to get this leg. We know for sure this is half of 6 because it's half of the equilateral triangle. This is the one that sometimes is hard to prove or hard to know that it's always times the square root of 3. But the square root of 27 is equal to the square root of 9 times the square root of 3. And we know what the square root of 9 is. It's 3 square roots of 3. So again, I got exactly what I thought there would be. And this relationship is true for all 30, 60, 90 triangles, that the one leg is twice as much as the other, actually the hypotenuse. This would be the hypotenuse side. So the hypotenuse is always twice as much as the short leg, and the long leg is always the short leg length times the square root of 3. You can see that in the other examples we did as well. So this idea is used often when there's a 30, 60, 90 triangle to find the lengths, only needing one side length to do so. And so that's kind of a breakdown of problem 4.3. And the whole point of problem 4.3 is to understand this concept of 30, 60, 90 triangles and how to find the lengths. Given one side, you can find the other two. This one is half of it. This one is the leg length times the square root of 3.